A very good morning, students. Today we will be seeing a very interesting topic in enzymology, that is how to measure the reaction kinetics of the enzymes. Let me go to the sharing of the screen. Okay, so when we consider the methods used in the investigation of the kinetics of enzymes, there are basically three methods. That is initial velocity studies, rapid reaction techniques, and relaxation technique. So today we'll be seeing the initial velocity studies. So initial velocity studies have been found particularly useful for investigating the kinetics of enzyme catalyzed reactions. It is one of the basic things that in the starting of the enzyme kinetic studies itself, scientists were depending on this. So the major reason why we use this method is that enzymes are often unstable in solution. So the restriction of investigations to V0 determinations give the best chance of avoiding any errors caused by the loss of enzyme activity in due time. Okay, the initial velocity of the reaction is usually determined from a graph of product concentration against time, or can be directly an instrumental reading which is known to be proportional to the product concentration. For example, absorbing units using spectrophotometer or spectrofluorimeter or a colorimeter or anything like that. And the rate of reaction could also be determined from the disappearance of substrate as the reaction proceeds, but generally it is considered a better option if we measure the appearance of something from an initial value of nothing rather than the disappearance of something from an initial or a large value, particularly when it is the initial rate which is all the more important. So here you can see the product concentration, a graph or the product concentration plotted against time for a chemical reaction. And you have to understand that the slope of the tangent that is shown here is the initial velocity. So the experiments are performed at constant temperature and pH using a method which enables the course of the reaction to be monitored continuously and preferably automatically. So that will give a rest to our hands, and the machine will do the work, and in the end we can get the values, and then further of your calculations can be done. The actual technique used will depend on the reaction being investigated. So if there is a difference between the substrate and product in the absorbance of light of a particular wavelength, spectrophotometric or colorimetric techniques can be used. The molar absorption coefficient of a substance, if known, is our work. Like it will enable the actual concentration of that substance to be calculated from an absorbance of reading, since absorbance is equal to molar absorption coefficient into concentration into the cell-like path in centimeters. So a wide range of oxidation reduction reactions are being, which involves particularly NAD, NADH or NADP plus and NADPH interconversions. They are suitable for spectrophotometric methods. So this can be taken as an example for you people to study. And the reduced forms of these dinucleotides have an absorbent peak at 340 nanometer, as shown in this figure over here. You can see that at 340 nanometer, when it is reduced, that is like in the NADPH stage, there is a peak absorbance you can see, whereas its oxidized form does not have a peak at this 340 nanometer. So it makes it easy to follow the course of their interconversion by monitoring the absorption of at this wavelength. Okay, so the interconversion of these substances may also be followed by something known as the fluorimetric methods, okay, which give greater sensitivity than the spectrophotometric methods. So the reaction where gases are involved or taken up as reaction proceeds can be investigated by something known as manometric techniques. So what does it happen? What does happen here is like the reaction is performed in an airtight vessel coupled to a manometer which records the changes in volume or pressure, and even ion selective electrodes like the oxygen electrode can be used when relevant to a particular reaction. Okay, so the other electrochemical methods like conductometry can also be applied wherever there are differences in electric properties between the initial substance and the product. So the methods which are not immediately applicable to the investigation of a particular reaction may nevertheless be used if the reaction is coupled to a suitable indicator reaction. Okay, so the principle here is that to add excess of the indicator enzyme, so the rate of the indicator reaction will be a measure of the rate of the reaction under investigation. For example, glucose oxidase catalyzes the reaction, that is D-glucose plus oxygen and glucanolactone, and H2O2 is produced. Here, the reaction can be followed by manometric or oxygen electrotechniques, but it is not suitable for investigation by spectrophotometric methods. The excess peroxidase is added to break down the hydrogen peroxidase that is formed. Then the reaction may be linked to the production of a colored dye from a suitable chromogen, for example, gaucum. Okay, the rate of appearance of the dye determined spectrophotometrically will be an indicator of the rate of reaction catalyzed by glucose oxidase. Okay, so an alternative to use of coupled reaction is to introduce an artificial substrate which, when reacting, results in a measurable change of color provided by the natural substrate. So, for example, para-nitrophenyl phosphate, it's a colorless compound which is hydrolyzed to yellow para-nitrophenol by the action of alkaline phosphatase. This is one of the common methods that we use when we are studying, when you are doing your enzymology practicals also. So, in your enzymology practical class also, we have the demonstration, particularly with this para-nitrophenyl phosphate. It's a colorless compound which is, when hydrolyzed, it changes to yellow para-nitrophenol by the action of alkaline phosphatase. So that's all with regard to your initial velocity studies for the enzyme kinetics determination. Thank you, students.